right. So, well, I've been recording the whole day because for some other stuff. But anyway, so the last concept I'm going to talk about is, from applications of gravitation. I don't know, how many of you actually heard of Kepler's law? And there are 3 laws involved. What are the 3 laws? And who's Kepler? Who's Kepler? A scientist, yeah? So, yes? What did he do? Something with gravity. Kepler. You should know Kepler. Google, when you have time, Google Kepler. He's the guy who works in the an observatory in Italy during the middle, in, I don't know, 18 some centuries. Yeah, very ancient. Yeah, long time ago, he worked. He worked under Tycho, who was from the royal family. So Tycho was the person who has a lot of money, and so he built an observatory in Italy. And so Kepler worked under him. So so Tycho liked to observe planets. So during the nighttime, he liked to observe how the planets like moving across the sky. So he kept a log of the planetary motion for each planet. And so Kepler was his assistant, and he continued Tycho's work, and then he just kept log of every night he just see observation, record the position change of the planets across the sky. So based on, and he, in addition just like writing down the observation, he also did analysis. So based on all this data, he was able to deduce that, contrary to what was believed at that time, they think that circle is a perfect, it's close to the God, so that the planetary motion should be in perfect circle. But then based on his observation, based on the data, he found that those planets, they do not move in circular orbit. In fact, they move actually in elliptical orbit. Elliptical, which means that it's not perfect. So he proposed something to the society, and it got a lot of I don't know. I mean, the people at that time, they believe in God. They are very faithful. They think that this is blasphemous, and then it's like. But this is actually pure science, just based on observation and data. But then at that time, people were saying that, oh, you don't believe in God. You're like you're against God and something. And some people actually got killed because they are thinking that they're playing a witchcraft or something. I don't know. But anyhow, those were the times and days. So what he found, based on his observation, he found that the orbit of the planet is not perfect. It's not a circle. It's actually elliptical. And let's say this is the sun. And the sun, traditionally is considered as the Almighty God. It has a symbol, it's equivalent to the God, but it's not at the center. You can imagine how shocked, most people back then, But then, based on his observation, he found that the sun is actually not at the center of the orbit. It's actually a little bit off the center. And this is, in one of the, it is actually one focus. So let's say this is Earth. This is the sun, so the Earth is actually rotating. It's actually rotating about the sun in this orbit, and not in perfect circle. Okay, so this is what they call the law of orbits. And if you know your math, I don't know what you cover. When did you cover the ellipse? Huh? Ellipse, yeah. So is that in elementary school? Huh? Oh, pre-cal? Okay. So anyway, you know the eccentricity, huh? Or say, I don't know. You can see I'm so old that I don't even know. I kind of lost track of, Anyway, well, we are recording, so I'm not going. Yeah. So this is. This is what we call the semi-major axis. So this has the distance a, and this is at one at one focus. So you can see that you have the lower orbit, which means that the Earth the planets, all planets moving elliptical orbits with the sun at one focus. This is based on his observations. It's not at the center, it's actually at, and it's not just the Earth. There are many planets, especially in the solar system. There are many planets that are orbiting about the sun, and sun is located at one focus. And this is the semi-major axis from the tail of the orbit to the center of the track. Okay, so this is number one. There are 3 laws, and the second law is actually based on the conservation of the angular momentum. And just say that the laws of areas. What does that mean? It means that the time rate of change of the area stays as a constant. So in math, what does that mean in math? Let's say A is the area. So time rate of change of area is a constant. And as such, and why is it a constant? Because it's actually coming from the conservation of angular momentum. Angular momentum within the isolated system has to be conserved. So when you have an object that's moving at a velocity and that's somewhere, and then you have this as as a rotation axis, then you can imagine that there is an angular momentum involved within that system. And because this is an isolated system, so angular momentum should not change, and as such that the time rate of change of area has to be a constant. And the implication or the consequence of that is that, let's say this is the distance between the sun and this planet, okay, at this instance. So within time delta t, the planets move from this point to that point. So it traces out this area within that time delta t, okay? So this is when the planet is away from the sun. Let's say if the planet has moved to this location, in order to keep the time rate of change of area to be a constant, what it means is that it has to actually move faster within the same time range, just so that the change in area within the same time frame would stay as same. So this is based on his observation. He was able to deduce that this is the law of area. When it's farther away, it actually moves slower. And when it's closer, it moves faster. Because it moves faster, so it can cover more area in order to be, to be equal to when it's farther away. Okay, so when it's farther away, it moves slower. When it's closer, it moves faster. When he found this, he didn't know there's a conservation of angular momentum, but then it is, this is based on the, based on the conservation of angular momentum. Observationally, he verified that. And there's actually, you can actually, do we want to derive it? We can actually just quickly derive it. I mean, it's very easy. So let's say this is the base. This is your R. So the distance connecting the sun and the planet, let's say is R. And we treat that as a height. So this is like a triangle. And if we want to calculate the area, how do we calculate the area? So the area is delta A. How do we calculate the area? If you have height, that's from this point to that point, that's all. And then you need this base, right? So this base, we call that, so if this is theta, then the change here is delta theta. So the distance here, that would be R times delta theta. The linear distance would be the radius times the angular change, if you recall from chapter 10. So something like this. So this is your R, right? And if you go from this point to that point, what is that translational distance? That would be R times theta, if this is your theta. So that's the same thing. So you have your R here, and then you have, so we have this distance, we call, so that distance is R times the change in angle. Okay, so you have your R theta, that's your base, and this is the height, so you can use the, your delta A is basically approximately equal to 1/2 the height, and then times the base of delta theta. So what we have here is 1/2 and you have your r squared, and then delta theta. We can do the delta t on both sides. So this is the time rate of change of area, and this is equal to 1/2 r squared, and then times omega, right? Delta theta over delta t. That is just your average angular velocity. And then, so what we have here is that how are we related to your angular momentum? If you recall, what is angular momentum? Angular momentum is r cross p. Okay, so you have the radius and the mass of the planet, and if it's moving with the velocity v, so you have this, and then you have your mv, and then your v can be expressed as omega r. Am I going too fast? But this is just basically, kind of refresh what you have learned. This is r cross p, rmv, rm, v is equal to omega times r, so you have your m, and then r squared times omega. Okay, so this is your angular momentum. So what we have here is that we have r squared over r squared times omega. So r squared omega is equal to angular momentum over the mass. So this delta A over delta T is basically equal to 1/2 angular momentum over the mass. So you can see that it has to be a constant because mass of the planet does not change, angular momentum does not change. So this has to be a constant. So the whole thing why the planet is closer, has to move faster, is because it's a result of conservation of angular momentum. Okay? So that's that. Any questions so far? All right, so this basically just gives you the rationale. If you didn't follow that, just after class, you can just read through the stuff again. So we're not introducing anything new. This is basically applications of what you have learned, and I think this is a very nice application of what you have learned. All right, so the last law is what we call the law of periods. So it has to be, so the periods involved. And how are they related to each other? So your period, the equation is this. The period of the motion square is equal to 4 pi square over capital G, okay, constant. Capital N, when I use capital N, usually indicate the object, the mass of the object that's being orbited. Not the so it will be this guy, not the planet. It will be this, okay? So the capital N, that will be the mass of the either the sun, for the solar system, or the mass of the Earth if we're talking about the sun, the Earth moon system, or Jupiter. Then that will be the mass of Jupiter and its satellite moon, okay? And then times r cubed. And r here is not the radius of the object. It is the radius of the orbits. Okay, so that relates the periods of the rotation to the radius of the orbits. So you have 4 pi squared over G capital N and then r squared, r cubed. Okay, so everything has to be in SI units. So the T here you have to convert it to seconds and then to calculate this. And again, this is basically based on the you can actually derive it using the centripetal acceleration and all that stuff. It's in the book, so I'm not going to derive it. So this is the important question that you'll find it's very useful to use because you can, the most useful application of this is that period is very easy to observe. You can just follow the motion of the planets, and you can easily find out the period. The radius can be inferred. The radius of the orbit can also be inferred based on the observation. So why is it this equation is very useful? That is because based on this information, you can actually infer the mass of the object. Do you know the mass of the, let's say, the mass of the sun? Do you know what is the mass of the sun? There's no way we can just go there and then measure it, right? We don't have a large enough, scale to measure it. So this will be a good way to actually infer the mass of the sun or the mass of a distant object because this and this are much easier to obtain than directly measure the mass of these of the planets or of the stars. Okay, so that's why this equation is very important, especially in astronomy. They use this to infer the mass of the object of the planet, and then just by using the observational data. Okay, okay. All right. Any questions so far? Okay. So so the Kepler's law. This is common sense. By observational angular momentum, lower the orbit is basically based on observation, and this is very useful. The third one is there's an equation that tells you how to utilize that. So we've been talking about Kepler's law, and then you have dealing with the planets orbiting around the an object. You can well imagine that. So let's say this is the Earth, and you can have a satellite. Let's say you have satellite, and that's like for communication, and they're just orbiting around the Earth, right? So it's almost like this is artificial moon that's orbiting around the Earth, and at the same time you have the moon. This is the moon that is actually orbiting around the Earth. So they all form a circular orbit, roughly like a circular orbit. So you have the moon, you have the satellite. They are forming this circular motion. Okay, what is the energy involved when you have a satellite or the moon that's orbiting around this object? What kind of energy is involved? When it's moving, what kind of energy is involved? There is a kinetic energy, right? The other thing is that there is a gravitational pull between these two objects. So there's potential energy as well. So in other words, the total energy of this object, be it a moon or a satellite, it is orbiting nevertheless, it should consist of two kinds of energy. One is kinetic energy, and one is potential energy, gravitational potential energy. So the question is, what is the expression for that? So let's say this object is some distance away from the center of the Earth. So let's say this is R. So in that case, what is your U? How much gravitational potential energy is involved? What is our U? If that's R distance away from the center of the Earth? Negative G. Okay, M. Over R, right? That will be the expression, the energy content in the potential energy. So that's negative Gmn over R. This is when the object that's some distance away, that's R distance away from the center of the Earth. What about kinetic energy? Since it is moving, it is orbiting around the Earth, right? So what will be your K? 1 half mv squared. So this m is this object, that's your m here, and this is your capital N. So 1 half mv squared. All right, so nothing unusual. So now let's see. So you have K. So the total energy of the system is K plus U. Now let's look at K again. What is our K? You have mv squared, and the whole thing is orbiting. So velocity and angular velocity, they are related to each other, right? And also there's let me see what is it I want to do. So, and also there's there's a gravitational force between it, and that gravitational force is actually equal to the centripetal force. So in other words, the force acting between these two, we have the magnitude of G, m, little m, and then you have your R squared. And it's pointing toward the center. This is the force, Gmn over R squared, with the magnitude. And that has to be equal to the mass of the object, and then times the acceleration of the object. And it's orbiting, so the acceleration is centripetal acceleration. So that will be m times your a. And what is the expression for centripetal acceleration? That will be v squared over r. So what we have here is that we have our Gn, capital N, over R, that's equal to mv squared, right? I'm just moving one R. So you have on the left-hand side, Gmn over R. On the right-hand side, it's mv squared. So what I'm getting at is that your mv squared is equal to this. So your kinetic energy is equal to 1/2 Gn, capital N, over R. And if you compare these two expressions, your potential energy is negative Gn over R. Your kinetic energy is positive 1/2 Gn over R. So your kinetic energy is not just by itself, it's actually related to your potential energy. And how are they related to each other? They are related to each other by this. Your K here is equal to negative 1/2 U. Okay? So your total energy of the system, which is K plus U, now becomes positive 1/2 U. Right? And so your K is equal to negative 1/2 U, and your E is equal to positive 1/2 U, which means that your kinetic energy and your total energy differ by a sign. Okay? So all this, if you think that just too, too much, then basically this is what you need to know. And your K is this. When you're talking about the object is orbiting around the other object. So your U is here, your K is this, and then your E is just basically K plus U. That doesn't change. Whatever that value is, whatever that value, it just happens to be negative K. Okay. So what I want to point it out is that this object is moving in this direction. So it comes with a velocity. If the velocity is not given, you can actually calculate your kinetic energy content because it is simply equal to negative 1/2 U. And you know that your U basically only depends on the mass of the object and also the separation between these objects. This scenario is different when you have a space shuttle that's going into or away from the Earth. When you have the space shuttle that's moving with a velocity, so you have a velocity. So this thing is not orbiting. It's actually going toward or away from the object. It's not orbiting. Then the kinetic energy, you still have to use 1/2 mv squared to calculate your energy. You cannot use this expression to calculate energy when the object is not orbiting around the object. This expression is good, is valid only when it is orbiting around another object. When you have a space shuttle, when you have a space shuttle or space vehicle that's going toward or away, you have to use 1/2 mv squared to calculate your kinetic energy. Okay? So that's basically just the difference between these two. Any questions so far? Okay, so I think I'll stop here.